Oh, yeah.
Okay, that's like a very genuine, legitimate. I was just waiting.
By the way, you're mispronouncing it.
I know. I think I know. What, how's it? Scheisse.
There's two S's there. One S is pronounced Z.
Okay. Well, Scheisse. Scheisse.
Yeah.
You gotta forgive me.
How about married?
It's my first language,
Married.
so it's like.
How about sign language?
No sign language. I'm not trying to joke here. I'm just saying it's my.
No, I appreciate it. I need to know how to cuss correctly, which is not something I thought I'd ever say because I do a pretty good job. By the way, if you ever learn any sign language, I took sign language in college one semester. And one of the first things that my teacher did was teach us all the cuss words because she's like, let's just get this out of the way. So it's really useful in like meetings just to alleviate some frustration. If you could just tell people off and they don't even know it, unless afterwards they're like, I know sign language. I'm like, oh shit. No, maybe don't do it. Don't do it.
Better Morse code because nobody can figure it out.
Yeah, just tapping on it. You should have. Okay. So we're about to get into chapter 5, and what chapter 5, the idea in chapter 5 is going to be pretty straightforward, and what I see its purpose as is moving us into the most important section, which has to do with this, the normal distribution. It's kind of like the big deal in statistics. What we did in chapter 4 was we looked at a couple of examples of a certain kind of data. Can somebody tell me? So in chapter 4 we saw like this would be how many pets do you have and the percentage of people that said that, yes? This is 4.1, 4.2. 4.3 was stuff like I picked 78 people and how was probably that 4 of them think of whatever, correct? Both of those situations, what kind of data were we dealing with? The Q words, yes? The Q words, the type of data?
Quantitative.
Yeah, they're both quantitative. And then more importantly is, if I break it down, are they discrete or continuous?
Discrete.
Totally discrete, yes? If I say how many pets do you have and you say 1.7, again, I am not coming to your house. I don't know what that is. It's 70% dog, 30% demon. I'm like, okay, that's great.
So sure.
Huh?
So sure.
Yes, exactly. So, and then of course with binomial, it's the probability that I have 11 successes. I would never say what's the probability that 10.3 people feel a certain way. Doesn't make any sense. So they're both discrete. So we're about to transition into continuous data. And obviously, it should be different. The work we do should be different in some fundamental way. Because, let me see, should I? Yeah, maybe I should. Let's do this. Yeah, okay. It's always a question what order I want to do the ideas in. So I'm going to try it a different order just because of what I just said. On the other side of the sheet we were just working on, everybody's got this histogram down there, right? There we go. So what this is, really quickly, let's see, if I want to do this semi-quickly, help me out. Let's do this real quick. Okay. So if I flip a coin 14 times, and it's a fair coin, what percentage of the time should it come up to be heads? 50%, right? So 50% tails. So if I wanted to probably get exactly 9 heads, it would be 14 flips, choose 9 of them to be heads. So I got 9 successes, and the rest are failures. Is that cool? Somebody help me out. Do that in your calculator for me. Yeah. 1, 2, 2, 2. I love it. Now, couldn't I do that for 0 heads? 1 head, 2 heads, right? What's the highest number I could calculate that for in this problem? 14, because I flipped it 14 times. If you said, what's probably flip it 14, you get 15 heads. I'm like, what the hell? No, it's not going to happen. So, what this table is right here, notice for 9, it's 0.122. Isn't that basically what we just got? So, of course, this I got real quick, and it only rounded to 3 places, but, we'll give them some leeway. I can then graph these, yes, and I did. I graphed these values here. Are you guys with me? So if you look at 9, it goes up to 0.122. Okay, so this is a discrete distribution because I can only have 0, 1, 2. I can't have 3.7, right? So this is discrete. Whereas if I was talking about lengths of branches that fell off a tree, how long could that branch be? Does it have to be 1, 2, 3 inches? Or could it be 2.97643367? Yeah. So now that would be a continuous distribution. It doesn't have to be normal, but it would be continuous. It wouldn't be bam, bam, bam. Notice also something really important here. What is the area of this rectangle? That's a very strange question, but what is the... Yeah, how tall is it? 0.122. Is everybody with me? How wide is it?
Oh, it's 1 wide.
1 wide. So isn't the area of it equal to the probability of that situation? The probability that it's 9 is equal to the area of the bar that represents 9. Does that, what I just said, make sense? Okay, I love it. Some of you guys are like, maybe. Keep going. All right, so let me... Okay. We'll look more at that in a minute, but let me keep going here. Anybody ever play darts?
Yes.
Yeah.
Anybody ever not play it but know what I mean when I say darts? I don't mean lawn darts that were...
Bar darts, right?
Say again?
Bar darts?
Bar darts, yeah, bar darts. Say that, you sound drunk. Sounds perfect. If I wanted to show somebody that I was really good at darts, what is the most common way I could show somebody I was really good?
Very tight spread of where you can land.
If I was to throw 1 dart and I want to show somebody I'm really good,
It hits the bullseye.
hit the bullseye. Now, why? If I had never played darts before and I throw a dart, could it go here? Yes. Correct? But what's the probability that it just happens to land there?
Oh, maybe that area of...
Holy shit!
Oh,
Okay. Sorry.
wow.
The probability it's going to land in that specific area is small because that area is a very small percentage of the total area. So if I just start randomly throwing darts at a dartboard and only count the ones that actually hit the board, what percentage of them will hit this? It's going to be related to the area of that relative to the whole area. So let's say the area of this is 5%, the area of the whole thing. Are you guys kind of with me? You with me? So what percentage of randomly thrown darts should hit here? 5% of them. Does that make sense? If I just was randomly throwing darts and we only counted the ones that hit the board, right? So if it hits here, I'm not going to count it. If it hits the kid walking by, I'm not going to count it, right? Poor little kid. Oh, wait. You guys all with me? What percentage of those randomly thrown darts should hit there? And let's say after each one I take it out, so it's not like going to hit something and fall. I would expect 5% of them to hit there. You guys agree? You can disagree. You can go, Jeff, you're insane, right? I really want this to make sense. So it is. So what is it? A higher chance that it would randomly hit this spot? Is there a higher chance? Of course, because it's a bigger area. That's why if a meteor falls to the Earth, the likelihood that it hits land is relatively low because most of the Earth is water. So it's the same exact idea. The probability that it actually strikes, and in fact, even if it hits land, it's more than likely going to hit some unoccupied land because a bigger percentage of land is not occupied. Believe it or not, humans, we tend to cluster. Okay, are you guys relatively with me? Okay, relatively. So two distinct situations where the probability seems to be related to the area. So if I call the whole area 1, this area would be 0.05, right? And maybe this area would be, I don't know, 1, 2, 3, 4, 5, let's say 20%, sure. The probability that a randomly thrown dart will hit here is 20% then. So if I have a visual and I call the entire thing 1, the probability of any slice of it is equal to the area of that slice, just like happened up there, just like happens here. Okay, maybe. So if I want to show somebody I'm really good at darts, I'll throw a dart, it hits here. Does that by itself tell the person I'm really good at darts? I think this is what somebody else said earlier. No, because it's still a 5% chance that would happen for anybody, correct? So then what do? Throw another one. If I do it twice, can anyone tell me what's the probability I hit the bullseye twice? Oh shit. Let me say it a different way. I want to hit the bullseye, and then I want to hit the bullseye again. And means multiply. So what's 0.05 times 0.05?
0.0.
I think it's 0.025. I think it's 0.0. Yeah, it's actually 0.0025. Yeah. Damn. So now it's a 0.25% chance that I suck and I just got lucky. So what's more likely? I got lucky or I'm good? Yes. And if I do it a third time, screw it. You're good. Holy shit. Are you kidding me? Now, you could alternately say, I'm going to draw a little area. I want you to hit right there. It doesn't, the fact that it's there doesn't mean shit. It's just the area of. So if I said, all right, now I want you to hit. So what do football players do when there's not a game, but they have like a thing? They have these little contests, right? They throw it through this hoop. Tennis players, right? I saw something where Federer, there was a bunch of little targets, and he had to hit the targets, bam, 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 and of course he did, because he's freaking Federer. But you guys kind of with me? So to show that you're really good, you have a target, small, archery, same thing, right? Sorry, I didn't mean to hit you with it. Okay, maybe. All right, so we all have kind of an intuitive sense. So how does this get merged into what we're all about? Well, here's the most immediate, simplest kind of problem. All right. Yeah, let's start with that one, but I've got to be careful. Okay. Anybody ever ride the bus? Yeah. Yes, okay, me too. So I've ridden the bus. It's a great experience. I love it. It's fantastic. Let's say we're in Germany. Why Germany? Because when I went to Europe, I was in Italy, and I waited a couple hours, and the train hadn't gotten there yet, and I said to somebody, where's the train? And like, it's gonna get here, it's okay, right? Go to Germany, it's like, the train's freaking there, holy shit. All right, so I don't know if you guys have ever been. It's a very drastic, I don't know if you agree with me or not.
No, I do agree with you. It's extremely weird.
I mean, if the train is 5 seconds late in Germany, it's like, what the hell? In Italy, it's like, yeah, it's fine, it's an hour. I mean,
punctuality is very much our thing.
Yes, okay. So, let me think. What was I even talking about? Good Lord, Jeff, go off on these
You're
tangents.
talking about riding the bus.
Yes. So if we're in Germany and the bus comes every 15 minutes, okay, right? The bus comes every 15 minutes. We get to the bus stop. How long should I have to wait if the bus is not there? What's the worst situation when I get to the bus stop? What's the worst thing that could happen? It just left. You're like, ah! So you're gonna have to wait 15 minutes. Yes? We're not San Diego where it's like, who knows? So the least amount of time I'm gonna have to wait is 0 minutes. That would mean I get there right when they're about to close the thing, and I'm like, I just walk right in. Yes? I waited 0 minutes. And the worst thing is I get there right when they close the door and they head off, and I'm like, shit, right? You like it? Now, if I get there and I don't see the bus, is there any way for me to tell? And all I know is it's every 15 minutes. Let's make sure that it's not like I just got to look at my watch and say what. Every 15 minutes, no matter what, it's just every 15 minutes. If I get there, I don't see the bus. Do I have any idea where I am in this interval? So, is it any more likely that I have to wait 11 minutes versus 3 minutes? Is it any more likely that I have to wait either one of those amounts of time? I really want you guys to, if I get there, there's no bus. Should I feel more like I'm going to wait 11 minutes versus 3 minutes, for example? Is there any reason I would feel like I have to wait more or less time? Do I have any way of knowing? No.
Knowing for sure?
No. So the probabilities are what's called uniformly distributed. No time is more likely than some other time. All I know is every 15 minutes. If I get there and there's no bus, no idea. It could be anywhere from 0 to 15. I know. Did it just leave? I don't know. Is it just about to get here? I don't know. Right? I really want this to make sense. So this
Early or late?
Say again?
Is it early or late?
Exactly. Now, when I say the word uniform, what's the first thing that comes to mind? Similarity. Say again? Clothes. What about what specifically? Be more specific. When I say uniform, you don't just think clothes. What do you think? Yes, where everybody at work has the same uniform, yes? So uniform, similarity, same. So a uniform distribution means all the situations have the exact same probability. Rolling a die, is that a uniform probability distribution?
No.
Is one more likely than two?
No.
So that would be an example of a discrete uniform probability distribution. Why is this one a continuous uniform probability distribution?
Because the measurement of time could always be more accurate than thus.
Yeah. If I wait 11 minutes, did I really wait 11 minutes? Or did I wait 11 minutes, 11.03976496? You guys semi with me? So that's why I can't use, for example, the binomial stuff, or I can't use those because those are for discrete situations. This is a continuous probability distribution. So if I want to know what's the probability I have to wait between 3 and 11 minutes, here's what's so beautiful about this idea. Do I have a visualization of the situation? Do I have a visualization? Yes, I do, right there. What did I say? If I make the area equal to what, then the probability is equal to the area of the slice related to that situation. If I make the total area what should all the probabilities add up to be? 1. I really want you guys with me on this. If I make the whole area of this block 1, have you guys drawn this yet in your notes? Draw this, there you go. There we go. You're like, notes? What? So, I love you guys. You don't have to take notes. You really don't. You should. Can you draw this in there? Right? What's that situation? It would be from 3 to 11. And then we'll do one better. We'll shade it in. Now, you don't have to be perfect. My scale sucks there. It's just a nice, quick visual anchor is what I call it. Just make sure 3 and 11 are actually between 0 and 15. That's a good thing. The answer to this question would be the area of this. Why can't I currently calculate the area of that rectangle?
You don't know how tall it is.
I don't know how tall it is. Now, what did we say a minute ago? I want the area of the entire block to be 1. And that would mean 100%. That's what all of them should add up to be 1. The area of the whole damn thing should be 1. How wide is it?
15, so it has to be point,
Don't overdo it. I don't want a decimal. What do you multiply 15 by to make the answer 1?
1 over 50.
1 over 15. Good old reciprocal, right? You with me? So you see how the whole damn thing is 1 over 15 tall, yes? Because it's uniformly distributed? Now don't say anything. Can you calculate the shaded area?
Yes.
Do it. Oh, wait.
Yep. Point.
Shh. Sorry, Sean. Just
Very
one.
good.
Zip it. So how wide is this area? 8. And how tall is it? Area is length times, in this case, height. So it's 8 15ths. If you do that, what do you get? Now you can tell.
0.53 repeat.
Neato. So about a 53.33% chance that I'll have to wait between 3 and 11 minutes. Okay, I like it. Uniform probabilities don't occur terribly often, and when they do, they're not terribly exciting. I mean, you can't beat this. Holy shit. What are we doing right now? Calculating areas of rectangles, correct? That's what this involves. That is what this problem involves. That's crazy. Now, in a minute, we'll talk about the mean and the standard deviation, and I will tell you this. There will be homework problems that ask you about the mean and standard deviation. I will never ask you about them on the test because we just don't use them very often, but I do have them in homework. I just want you to know they exist because what did I say? Every time we get a new distribution, what are the 2 most important things to know? The mean and the standard deviation. So I want you to understand formulas exist. And I want to see your reaction to the standard deviation formula. See if it is what I normally get. It's bigger on the inside.
Real quick, Professor?
Yeah.
Sorry, is that graph called uniform probability or uniform distribution?
It's a uniform distribution, but if you want to be more precise, this is a probability distribution that is uniform.
Okay.
Yeah. So it's like a normal distribution, a uniform distribution, yeah. Let me see, what other colors do I have? Not many. Poor little Jeff. Okay. So let's do. Let me ask you this. What do you think the probability? Let's see if you guys get this. Well, real quick before I do anything too weird. What's probably x is greater than 13? So again, you always go back to the picture that represents the situation we're in. That's this, yes? So 13, greater than 13. Why is it a little bit of a weird question? Because what's the most it could be? So what's greater than 13 would be this little slice here. Yeah? So that's the same thing. How wide is that? 2 times 1 over 15. And then whatever the hell that is. It's 0.13.
Exactly.
Yeah.
How did you do that so fast?
Just divide this by 4, because that's 8, and this is 2. Math tricks. I'm a math boy. All right, now, let me ask you a really, really strange question. In both cases, what's the physical thing that led us to get the answer? In any probability question, For a continuous distribution, what did we do physically? What did we do geometrically to get the answer? We found the area. Beautiful, right? So let me ask you this. Keep that in mind. It's a trick question. Not really, but sort of. What is the probability that x equals 7? Hold it. People think. So I'll get people telling me it's 7 out of 15. No, makes no sense. What is the area of the line that represents the situation, the 7? What's the area of this line? How wide is the line?
1.
That would be like from 7 to 8. How wide is that line? 0. Doesn't it go from 7 all the way to 7? Yes. Really, it has no width, does it? Think about it this way. Can anybody tell me how many numbers are between 0 and 15? How many numbers? Not whole numbers, not integers. How many numbers? Infinite number. Isn't 11.394 in there? Isn't the square root of 6 in there? I mean, anything is only from 0 to 15. Yes? There's an infinite number of things, yes? If there were 20 things, what's the probability I pick one of them? 1 out of 20. There's an infinite number of things, so what's probably I pick one of them? 1 divided by infinity. Anybody know what that is by any chance? It's basically 0. So again, the answer to a probability question, when I have a continuous distribution, and I got the picture, it's going to be the area related to that question. This has 0 width. So the answer is 0. There's an infinite number of things. So to be really, really honest, I really want to make sense. If I divide by bigger and bigger and bigger and bigger, right? What's 10 divided by 20? A half, 25. What's 10 divided by 200? 0.05. What's 10 divided by 2,000? 0.005. So what's 10 divided by stupid big? Stupid small. Right? So what's 10 divided by infinity? Well, it's freaking 0, basically. But to be really honest, this is actually called iota, which a lot of my colleagues will kind of deride me for saying this, and I don't give a shit. It is known as, so you can think of it as the smallest positive number. Think about the smallest positive number for a second. What does that mean? It's not 0, it's just above 0. Do you know what number that is? I don't know. 0.00001. That's pretty close to 0, correct? Is there a number that's closer to 0? Yes. All right, now everybody, I will stop with it. I'm sorry. I will stop. You don't have to know that. I just wanted to throw this out in case anybody was curious. When we see this, we will say 0. Because the answer is related to the area, and the area of a line is 0. Okay, I like it. Okay, let me make sure about something. Let's do a little rapid fire session real quick. Because if I can draw the picture, and then I can draw the question, it's easy. I'm just finding areas of rectangles in, right? That's it. That really is all it is. So let me do a couple. Oh, you put it there. Quick fire things real quick. Let's say I have something that goes from 5 to 12. How tall will that be if it's a uniform distribution? I will tell you this real quick. The answer is not 1/12. It's 7th, 11. See, I started with an example that started at 0. That could lead people to get the wrong idea. It's not 1 over this number. It's 1 over how wide it is, correct? I really want to make that clear. So if I had a distribution that went from 4.2 up to 11.9, oh shit. How tall will that be? 1 over 7.7. You with me? What if I had one that went from 5.5 to 6? 1 over 0.5, which is? Right, this is 1/2. 1/2 times 2 is 1. So the area is 1. You with me? So it's always the width 1 over that. It's the reciprocal of the width. That's what I do to multiply to get 1. Okay, maybe. Once I got this, then I can answer it. If you ask me what's probably that it's between 5.6 and 5.9. All right, that's easy shit now, right? That's easy. 5.6 to 5.9. That is 0.3 times 2 is 0.6. Next. Okay. Now, yeah. So let's do this. On the other side of this, question number 3. Let's do that together. And then, you're not going to believe this, but I have a handout that I'm going to ask you guys to work on together that goes over this kind of stuff here. So we know that the time it takes Jeff to find his car keys is uniformly distributed between 1 minute and 12 minutes. Okay. So what would the distribution look like? Stay with me now. Start at 1. Go to 12. And how tall would it be? 1 over 11. Kick ass. So whenever I ask you to draw the distribution, I'll be nice. I'll say indicate the height, because without that, it's not complete. So now I can use that picture you just drew to answer any probability questions I throw at you. So don't say anything. Just take a minute. Probably it's between 7 and 11. Don't say nothing. All right, who's got that? How wide is the shaded area? Well, it's 4 wide times 111, so 4 over 11. Yeah, so it should be 0.36 repeating, right? Or you can write 0.3636, or you can write 36.36%, whatever. Okay. Any of those are fine. Part C, I always get people that jump to what they think the answer is going to be within the first 5 minutes of looking. So would it be 5 over 11? Nope. So within the first 5 minutes, what is the width of that? 4. So again, it's 0.3636. Are you guys okay with what's happening? Okay. What about more than 12 minutes? 0. Assuming this is true, yes, which is a big assumption, but oh well. What about probably takes me exactly 8 minutes? 0. Okay. So. Let me give you this. This little dude, one side has got a bunch of little blue mountains. Don't worry about that side yet. Obviously, that's going to be the normal stuff. The other side looks a lot like this, and it's got problems I want you guys to work on. I'm going to put you guys into groups so I can finally shut the hell up and let you guys talk to each other. really sorry if you're comfy in your seat. I'm gonna do my thing. I'm gonna put y'all into groups. Yes, sorry.
Why would it, for E as the baby, why was that 0?
So if you draw it in, oh sorry, what was it? 1 to 12, and you got 8. There's the thing.
So the line.
Yeah, it's just a line, no area. Yeah. Let me see. Which will be neat because you have no way to do it right now. So let me catch up to you guys. Help me out. For number 1, what's N? 26. What's P? Q? And for number A, good old number A, what's X? 5. I love it. Okay, so now it's just throwing everything into the formula, right? So I got 26 people. I want to choose 5 of them to be successes. So remarkably enough, I have 5 of these, meaning I have 21 of those. So the 2 exponents always add to be the total number because we're taking a total number and putting them into groups, right? We're not killing anybody. We're not throwing anybody away. We're not making people. So they always have to add to be the total number. When you throw that in the old calculator, what do you guys get? 1750? Okay. So you guys got? Okay. I'll crowdsource that. I love it. Everybody with me? So I desperately want the binomial. I personally, I'm a weird person, obviously. I love math and all that shit, but I'm hoping some of you guys can appreciate the fact that captures, that's like a sentence. I got 26 people. I choose 5 of them to do this thing. So I got 5 of them doing this thing, and the rest are doing the other thing. I mean, I'll stop. Okay. This one sucks a little bit, but not as bad as it first seems, because I could do the probability of 3 plus the probability of 4 up to 20. And, we're like, no, I'm not going to do all that shit. I'm going to do 1 minus. What does more than 2 leave out? 2, 1, 0. So I'm going to figure out the probability of 2, the probability of 1, and the probability of none. Add those up. That answers the opposite question, so then I just do 1 minus that. Any damn time the opposite probability question has less work, I'm going to do that shit. And then I can do 1 minus what I get to answer the actual question. That's just we know that. You knew coming in the probably going to rate is 11%, probably not going to rate is 89%. We know that coming in. That's all we're doing. So what'd you guys get for the probability of 2? 0.0324? Is that what everybody got? I'm trying to see if I can do this without using my calculator. Probability of 1? 0087. Is that what you guys got? Yeah. All right, somebody else tell me what's the probability of 0? 0011? Neato. So when you add all those up, you get 0.4 something 22? 0422, is that right? So I want to do 1 minus that. That's the probability that up to 2. So the probability more than 2 would be 1 minus that, which is point. Good. Okay. And it makes sense. I mean, I would expect a decent percentage of the time to get more than 2 out of 26. Okay. Then we got the mean and the standard deviation, the 2 beautiful little equations, n times p. What do you guys get for that? 5.98. And then the standard deviation is n times p times q. Well, did I start you up? I did. If you start me up. And then 2.146. Is that what you guys got? Kick ass. All right, good. Now this is kind of neat. I was nice up until now. Here I was a little mean. I want to make sure. Let me do a little side thing here, and you're all like, do whatever you got to do, man. You're the teacher. All right. If I flip a coin 300 times, right? What's the most likely number of heads? 150. You guys agree? That's the most likely number of heads I'm going to get if that's a fair coin, correct? Okay. What's the probability that I get 150 heads? You don't write this down. Just watch. That would be this here, right? If I want to get, you guys with me? 300 flips, choose 150 to be heads, so 150 successes, 150 failures. You with me? That probability, do I still have it here? Is less than 5%. Jeff, wrong way. Do you see that? The most likely thing to happen is less than 5% chance of happening. Why? Well, how?
Because there's just so many things that could happen.
0 to 300. It pretty much looks like, well, not even that. So, Jeff, you can do it, buddy. 0, 300. It looks like this, where this is 4.6% tall. So something being unusual, I can't calculate the probability of specifically it and saying, oh, that's less than 5%. I need to figure out what region has a less than 5% chance of happening, and is it in that region? I really want this to make sense. How many people are exactly 5'9"? How many American men are exactly 5'9"?
Less than 5%.
Holy shit. I would say 0 are exactly 5'9". But what is the most likely average height to get if I pick a group of men? 5'9". Okay. So my point is, do not calculate the probability of 8 here. That doesn't make any sense. It makes no sense. Where does unusual start, right?
More than 2 standard deviations away.
Yeah, so what's 2 steps up and 2 steps down from the average?
Up is 10.2716.
10.27 blah blah. And down is 1.68 blah blah blah. Okay. So is it unusual to find 8? Nope. Why? It's within there. It's less than 2 steps away. It's in the usual area. So again, we knew from day one, if I take a sample of Grossmont students, I would expect their average age to be close to the actual average. We are just getting more and more sophisticated in our understanding of what the hell close means. Close is a freaking arbitrary word, right? Is Earth close to Mars? Yeah, on the scale of planets, right? Right? Am I close to you? Yeah, on the scale of where everybody else is in the universe. Yeah, I guess semi. All right. Sorry, I'll stop. So close. We try in statistics to quantify what close means, and the thing that makes the most sense is to use the standard deviation, the average distance things get. Okay, I'll stop. Looking at number 2. I'm really hoping these kind of problems are nice. So from 22 to 39. The great thing about a uniform probability distribution is I have to actually say it's uniformly distributed. So then you're like, oh, I use that. How tall is it? 1/17. I love it. So it probably takes more than 28 minutes. What's the area of that rectangle? 11 out of 17, right? Is that cool? And then whatever the hell that is. 0.647? 1? Holy crap, Jeff. My 1's kind of falling out. Okay. What about less than 22 minutes? That's an interesting question. 0, because the area back here for anything is 0, right? Now this is a really, this is bad in 2 ways, but the answer to that would be 0, but it's really, really 0 because 8 is even less than 22, right? So it's like 0 double overs, which is still 0. Okay. All right. Don't get too excited. We're not leaving yet. Any questions on this entire thing? So this is chapter 4. This is chapter 5, right? This is not all of chapter 4 because the XP of X stuff is there, but we had its own handout for that anyway. So. Okay. Recording? Yes. Okay. So, if you'd like, you could head back to your desk. We're going to look back at this thing real quick, if I can find it. Dadgummit. Here it is. Yeah. All right, sweet. So, I always, pretty sure by now you understand that I always try to derive formulas. I try to show you where they came from. If you don't totally understand the derivation, you at least want to understand when we use what formula. I also try to show you like concrete examples of why things work the way they do. So in this case, when we have a continuous distribution, if I can draw the situation and make the area 1, the probabilities are just equal to the area related to the probability of that's related to the question. There it is, Jeff. So in a uniform curve, and here's basically the idea. This is b minus a, so the height would be 1 over b minus a if you want to make it all formulaic. All of the subsections are frickin' rectangles. That's why they're so easy, right? Yeah, I'll have to come back to that. Darn it, I will. So when I have a normal distribution, look at a possible subsection right there. Look at that subsection right there. Do we have a geometric formula for that shape? Hell no. Right? What about, this shape here? Do we have a formula for something with a curvy hat? It's a rectangle that's got a curvy hat on top. What is the curvy hatted rectangle formula? Do you guys remember that from geometry? No, you don't, because we ain't got that shit. So we're going to need some help. The idea stays the exact same. The answer, if I want to know what the probability is from a negative 2 z-score to a 1.39 z-score, it's still going to be the area that catches. That's still the answer. But do we have a simple way to calculate the area? No. Even if you knew calculus, you actually have to know calculus 2 to be able to calculate it directly. Thank the gods, I'm not going to teach you calculus 2 real quick. Oh, 10 minutes. Let's go, calc 2. What I'm going to give you is a table that we can just look up certain z-scores to find the areas. And I should have brought them with me, but I didn't print them out. I didn't think I'd make it this far, to be honest. So, one thing before I get past uniform curves. So when we get, chapter 6 is going to be all about normal distributions. They happen a lot more often than we think they do. Heights are normally distributed. IQ scores are very stupidly normally distributed because we force them to be. They don't just happen. We force them to be normally distributed. Okay, so IQ scores have a lot of issues, but they're there.
What do you mean you force them?
We standardize things to force them to be normal. We kind of curve things to be that way. Yes, so they're not naturally that way. They're not naturally occurring things. Anyway, we won't get into the nitty-gritty of IQ scores. One last thing I want to talk about with uniform distributions. This should make a ton of sense. The first part of this should make a ton of sense. Let me see. If what was it? Yeah, I think that was, wasn't it 0 to 12? Let's say it takes me from, it's not this. Let's say it takes from 0 to 12 minutes to finish a job, uniformly distributed. So maybe 0 minutes would mean you come in and somebody already did it. And 12 minutes means no part of it was done yet. You guys semi with me? I just want to make a quick physical. What's the average amount of time to do the job? Doesn't it make sense? If it's from 0 to 12, the average should be 6. On average, 6 minutes. Are you with me? So if I did this job many times, sometimes it'll take me more than 6, sometimes it'll take me less than 6. On average, 6. So the average for a uniform distribution from A to B, the average is just A plus B divided by 2. Kick-ass. That only makes sense. That's my hope. So if the bus comes from 0 to 15 minutes, what's the average amount of time people wait? 7.5 minutes. That makes sense. Here's the neat one. Let me see your immediate reaction to this. Here's the standard deviation formula. Okay. Does anyone have an immediate reaction to that?
Is it always going to be 12?
Say again?
Is it always going to be 12 divided by 12?
Yeah.
How's that number?
There you go. Okay, that's the question. All right. I don't know if anybody watches Doctor Who, but it's like the doctor waiting for somebody to say, it's bigger on the inside. I can, in fact, I will, let's see if future Jeff remembers to do this. I have the derivation of this formula. I will put it up in Canvas. It does involve calculus. So if you don't know calculus, you can just kind of look at it and go, all right. But if I were a student in this class, I would immediately gravitate to what the shit is 12 doing there? What do you mean 12? What sense does that make? I don't blame you. This is what I mean. So I will post that. And again, it is calculus based, and you can look at it. It's fantastic. Some of you guys know some calculus. Those are the formulas for the mean and the standard deviation. Those are always the two kind of most important summaries I can make of a two parts of a summary I can give somebody about any set of data. And like I said, I am not going to ask you a question about these on the quiz or the test, but they are in the homework. It's just plug and chug. So if I went from 10 to 16, I could plug, what is A? Up here, let's see who is paying attention. What's A? 10. And B is 16. So it'd be 10 plus 16 divided by 2. Beautiful. And then this would be 16 minus 10, 6 squared, 36 divided by 12 is 3, so it'd be the square root of 3. That would be the standard deviation. I love it. Okay, good. Now, last thing for today. Holy crap, I wanted to let us out earlier, but too bad, Jeff. Because if I let you out early, I let me out early. Last thing. I already said this. Yeah, that's true. So the standard deviation, normal distributions, oh crap, happen very, very often in the real world. So we're going to have to develop, if I want to know the probability I'm from 1.12 to 1.74 z-scores, if I want to know that probability, I can't do the same thing we did with uniform because the shape is not a known geometrical shape. Do you guys agree? This is like a crayon that's been out in the sun. It's just kind of melted. What's the area of the melted crayon? I don't know.
Everywhere?
Dude. So that's why we're not going to do the calculus. We're going to have a computer do the calculus, and then I'm going to give you that table that's got. So basically the table is going to be, if I want to look up 1.1, I would look at 1.1, and then I go over to 2, and it would tell me the area. It's going to tell me the area below that. So then we have to figure out how to use that information. So I'm going to bring that table next time. We're going to do the other side of this, wherever that went, Jeff. Oh, here. With all the normal curves and so forth, right? So I'm going to bring the chart. This is really just going to be getting used to how to use the chart. So we're getting into the most important chapter in Statistics 1. Chapter 6 is the most important chapter. I see everything we've done so far has gotten us ready for this. So that's what we're getting into tomorrow. That's enough for today. So, the next quiz. I think we'll do a quiz on chapter 4 on Monday. I want to give you guys the weekend to kind of catch up on homework stuff. Okay. All right, so I'll see you guys tomorrow. Next Tuesday, of course, is 4th of July, so we'll have another Tuesday off next week.
And next Wednesday is the test.
Yay, Jeff! Thank you.
Yeah, I'm sure that's a good point. Must have just been.
Yeah, I don't think I am, but we'll see. Tomorrow I'll have a practice test either way. Oh, don't forget. Okay.